the first measure of interest to us is what is called arrival rate. I will use the Greek letter lambda. Let us say lambda is the mean arrival rate. What I mean by that is if people arrive, you keep observing a system and you find on an average every hour 12 people arrive, then we are saying the mean arrival rate is 12 per hour. That is what we might say. So, this is the equivalent of the demand that we talked about in the earlier capacity analysis. We said our daily demand is so many vehicles and all that. Same way we can look at this. The second parameter of interest, I use the Greek letter mu. Let me call it as mean service rate. Remember, we always talked about process time. So, if the process time on an average, so if on an average it takes 4 minutes, then we will say the service rate is 15 per hour. So, these are the two measures we will always remember. In any system there is a demand which can be represented by mean arrival rate. In any system there is some processing happening which can be represented by service rate. So, we have lambda and mu. Okay. Now, let us look at some measures of interest to us. The first measure of interest is utilization of the resources, which we have always been calculating in the deterministic case also. So, let me use a Greek symbol rho and let me call it as utilization of resource. So, in a case of a single server, we are now looking at only a single server queue, which is the simplest, which we can easily think about. The utilization is generally given by the ratio of the lambda and the mu. Obviously, we want to have a better utilization of resources. This is an important business concern. So, we will keep that. We will introduce LQ. Easiest way to remember is length of the queue. That is why it is called LQ. In other words, we are asking on an average how many people or number of customers waiting in the line. We are interested in utilization because a lot of business problems they are very seriously interested in utilization. Customers do not want to wait too long. A large queue in any system reflects badly on capacity and the system. Therefore, we are interested in LQ. What we will do now, I will write a formula. Let us not worry too much how the formula came, but we will worry about what is this formula trying to tell us. I think that is more important to us. So, if for this single server queue, if I have to calculate what is the queue length, the formula will go like this. LQ is a ratio of lambda square mu times mu minus lambda. So, we will just use this formula. As we have seen, the queue length is a ratio of lambda square by mu times mu minus lambda. Now, let us look at this formula. What is it trying to tell us? The first thing that we notice is if mu and lambda comes closer to each other, then in the denominator mu minus lambda will go closer to 0, which really means that this number is going to become very large. And the limiting condition is if mu is equal to lambda, the denominator becomes 0 and mathematically it is indeterminate. It is very large. So, the first implication that we can get out of this formula, simple formula for a single server queue, is service rate and arrival rate cannot come closer to one another. Now, we also remember that utilization was nothing but the ratio of lambda and mu. Therefore, if lambda gets closer to mu, it means the lambda by mu is going to become 1. Both are equal. So, 100% utilization. So, even that is not a good idea. So, these are the two very important implications that we must remember. So, just to summarize, as the difference between the service rate and arrival rate narrows down, the queue can build longer and longer. And secondly, since the utilization is the ratio of these two numbers, lambda by mu, What it means is at higher utilization the Q gets very large, and when both lambda and mu are exactly the same, utilization is 100% and the Q becomes infinite. This is in stark contrast with what we have seen so far. This means that when we deal with uncertainties in demand and service times, we should not design a process for 100% utilization of resources. If you may recall, in some of our earlier examples, we were computing the utilization at the bottleneck station to be 100. That was because it was a deterministic process, times are all deterministic, demand was known with certainty and so on. Whereas in the case of an uncertain demand and process time, it is managerially unsound to go for 100% utilization. That is a very important message we are getting out of this simple single server queue and the formula that we have seen now.